This is, guys, this is our Taylor project. And the point, shh, guys, David, put your feet down, please. Feet down. Okay, guys, we're winding down to the end of the semester. And this is what we're doing. We're doing the Taylor project today and tomorrow in class. After that, you're on your own. You should be able to get it done really before Friday. I would recommend it. Then I will teach Taylor polynomials, but I'm hoping that you will actually do this, because if you do this, you'll have a better understanding of what it is. It is a free response question on the AP exam. At least one, sometimes more. Okay, so if you want to get a 5 in the exam, this is one that you can easily do and get your points. Now, last year the scores were high. I think it was 4.7 out of 9. Usually about 1.3. So we are going to do the project today and tomorrow, Thursday and Friday. Thursday I'll actually teach how do you find a Taylor polynomial. And then we'll work on AP problems on Friday, Monday, and Tuesday. And your test, which is actually a 2-day test, is I think Wednesday and Thursday. I have to go through your more recent calendar. I don't think this is up to date. And then we have exams. So there's not a lot of time left. And the exams will be chapters 1 through 3 and then chapter 8. For sure you'll have 2 free response questions. One will be a parametric vector type problem, and one will be a Taylor polynomial. There's one part of it that we're going to skip, and it's the error. It's called Lagrange error. And we will do that in May, right before the exam, because you won't remember it anyway. Okay, Kevin? Okay. So here's what we're going to do. I'm going to get you started on it. Now, you guys need to learn to read. It is a critical skill, Natalie, for college. James, we're over here. Maybe I should have you guys read it instead of me. It says, we've been investigating, and you probably forgot, this summation of x to the n. Do you remember that? What is that? Natalie, I need you focused. This stuff is not easy. This is a summative grade, and we grade very harshly. The packets I haven't done, and I'll be probably grading that harshly since all the answers are in the book. But it's 1 plus x squared plus x cubed. What's special about this? It's geometric, okay? I even wrote it down there. It's geometric. What's a? 1. The common ratio is x, and so this sum is a over 1 minus r. So it's 1 over 1 minus x. Do you remember when I graphed that? I put this in, and I put this into the graphing calculator, and it only, these two functions are only the same when x is between 1 and negative 1. Outside of that, it doesn't work. It doesn't converge. Remember that? Now, I really stressed that you needed to do 8-6. We found families. We found relatives to 1 over 1 minus x. We did 1 over 1 plus x, didn't we? We wrote it as 1 over 1 minus a minus x. And we found that power series for this function. And we integrated, and we differentiated, and we multiplied by x or x squared. We did a lot of different things, but everything was related to this original function. So they were families. Okay, we found more geometric series if we differentiated and integrated the original series. We ended up getting logarithms, because the antiderivative of 1 over 1 plus x is the log of 1 plus x. Right? Remember that? The integral of, whoops. The integral of 1 over 1 plus x dx is the log of 1 plus x. Okay, so we found, if we could find this power series, we wrote it out term by term, and we integrated it term by term, which was very nice. Okay, so we found power series for many functions, but only the relatives of this function. You can differentiate, you can integrate, you can multiply by x or x squared. You can do a whole bunch of things to that. But I can't get e to the x from it. I can't get the sine of x from it. So that's what we're going to do. We only know how to find those functions that are related to that series. They have to be relatives, even if they're distant relatives. What about e to the x? What about the sine function? What about the cosine? How do we find power series for those? Taylor polynomials and power series are one and the same. When they ask you for a power series, they're asking for a Taylor polynomial. They're both the same thing. These are all power series because, why are they power series? Because, what's a series? We forgot what a series was. What's a series? You add them all up, right? And what's special with these? These are all powers. Remember, powers have to be whole numbers. You can't have negatives, can't have fractions, but it's x to the first power plus x to the second power. That's why this is called a power series. I might have to have you move it. Okay. Can we do other series? Can we do e to the x? Yes, we can. So we're going to move on to the next part. Uh-oh, this might not have copied it well. Oh, I hate that. So you can read the next part. I'm going to find this and fix it. Okay. This is not a big, hard project. It's a math project, which is different. Okay, guys? Oh, I think I did too. So, hang on. Yeah, I did. Before I'm going to leave this up. Okay. Now, what happens in math a lot, Kevin, is that people get credit for something they didn't do. And it's probably true for Taylor and Maclaurin as well. They, for some reason, got credit for this investigation we're going to do today. They are famous mathematicians. They did do a lot of stuff, but they may not be necessarily associated with this. I think you're going to have to go look it up. And by the way, I do not recommend using Wolfram or any other internet source to help you find these Taylor polynomials because I won't give you credit because you actually have to show me how you get these polynomials. So, people just copied and I could tell they copied and that was it. Monday the 9th. Oh my God. Matt, I think it's time for you to change places. Okay, so Taylor and Maclaurin, yes, they decide they want to investigate further. Guys? Justin? No. Okay. Here's what we're going to look at. We want to find a power series for e to the x, cosine of x, and sine of x. So if you take a function at a point at x equals a, so here is a trig function. Doesn't really matter where we do this. But what's true about the slope here? So here's f of x. I want to have a polynomial to approximate that. What would be true about the slope of my polynomial? Well, it's a positive slope in this case, but what if I'm over here? It's negative. But what would be true? I'm going to say I want p of x to be approximately equal to f of x. What would have to be true? Well, what would have to be true about the functions here? At this point, wouldn't they have to be the same? Okay, so p of a, my polynomial at a, has to equal the value of the function at a. In fact, I did the first approximation. This is the linear approximation to the curve, right? As long as you stayed reasonably close to that point when we did these linear approximations, this was a pretty good approximation. We can approximate better than that. We can maybe make it quadratic or something like that. What's true about the slopes at this point? Wouldn't they have to be the same? Isn't the slope of the tangent line equal to the slope of the curve there? They have to be the same. So p prime of a has to equal f prime of a. What do you think is going to be true about the concavity if I try to put a polynomial in there? If I try to put a quadratic one in here, I'm certainly not going to have it concave up, am I? I'm going to have it concave down. Of course, now it fails over here. doesn't it? But what if I put a cubic in there? Would that maybe work? What if I did a quartic? A quartic might, I do this and come back down. Okay, just it. I'm going to have you move over there then. I don't care. Guys, this is a big, major project. It's a major part of your grade. Okay, what's true about this? Because you're not going to understand how to do it. And guess what? We're not available tomorrow morning. So what's true about the second derivative at A and the function? They have to be the same. What do you think is true about all the derivatives? They're all the same. So the third derivative at A has to equal the third derivative of the function. Okay? So that's what we're going to have you do. We're going to have you approximate this. Okay, so shouldn't this have the same concavity at that point? What about the rest of the derivatives of the two functions? Shouldn't they also be equal? The polynomial, the power series, you're trying to use to approximate this function. And to me, it's amazing that they are equal. Think of the geometric one, 1 over 1 minus x. Okay, James, over there. No, that's not what we're doing right now. Maybe we'll stay there for the rest of the semester. We'll see what happens. Well, it's next to be moved. Because it's wasting time and it's wrecking the video. And Mrs. Thurston doesn't like to do the video, so this is what you get. Okay. Seems to make sense that they would not only, it would be the same functions equal to the same point, but all the derivatives must also be equal. So using these thoughts, let's see if we can find an infinite series to any function. You're going to use these conditions right here. The fact that these all have to be the same. The first derivative of the polynomial has to equal the first derivative of the function. Most likely on the exam, they will not give you the function. They'll actually give you just the derivatives, which makes it, of course, hard. And there's a lot of information. Okay, so let's start with the cosine curve. Whoops. Question? Somebody's going to ask me something. No? All right. Let somebody say something. Okay, let's start with the cosine curve. Can we find a power series that's equal to the function? Let's first start with a linear approximation. You just do what it says to do. And it says, remember how to find the linear approximation to any curve? So if I graph the cosine curve, and we're going to do this at x equals 0. This is, by the way, called the Maclaurin series. You hope on the exam it's Maclaurin, because that means we're going to center our polynomial at 0. So I'm going to graph the cosine curve here real quickly. And this isn't too hard to do. I want the linear approximation. Marcus, you need to go out in the hall and compose yourself. And Matt. Okay. What's the linear approximation? You remember how to write the equation of the tangent line at 0? Well, this was pretty easy, right? But let's write, now you can use this linear approximation, or you can just do y minus y1 equals mx minus x1. And you want to solve for y. So the chief reader on the exam prefers that actually we do the linear approximation this way. Y is equal to y1 plus the slope x minus x1. And let's make that a little fancier. Let's go to function notation. So this is going to be my linear approximation, call that L of x, is equal to f of, in this case, it's f of 0 plus m, and then it's x minus 0. There's reasons for writing that out like that, because there's patterns we're going to look for, and you're going to start seeing it. Okay, so if f of x equals the cosine of x, then what's f of 0? The cosine of 0. And here you have to evaluate them. I'm sorry, no, you on the free response you don't, but you have to tell me that's 1. So you can't leave all that stuff in there. What's the derivative of this? Let's see. F prime of x is equal to negative sine of x. So what's f prime of 0? Negative sine of 0, which is 0. So the slope is equal to 0. Well, you could have told me this equation before, couldn't you? What's L of x equal to? It's equal to y1. It's f of 0, but that's not 0. It's 1 plus 0 times x minus 0. So it's just y equals 1. Okay? Well, guess what? That's the first question on the handout. So it's not that bad. But notice what it says to do. It says to write a, when you do a project, a science project, you always had to where is it? I might have missed it. Did I miss that piece? Oh, no, never mind. I changed it. Ignore that. Okay. That was question 1. Do you think we could do better? What if you did a quadratic? Okay, I'm going to try and do this with my highlighter. What if I did a quadratic approximation? Well, it's pretty good. It fails over here. Justin, you need to leave. I need you focused here. This is not about playing games, okay? Okay, is a quadratic approximation better? It's going to be better. I don't know what the problem is. I know we come back from vacation, but we have a lot to get done before exams. It is huge on your exam. And it's huge on the AP exam. So we got to get this. If you understand where it comes from, and when you see the big formula, it will make far more sense to you. It still may not make that much sense, but it'll be better than just, here's the formula, let's do the problems. I could do that. I think this is a valid project for you guys to do. Okay, so we're going to try to approximate the second. We want another approximation for this. Well, we're going to look at the first derivative. We know the first derivative should be the same. Second derivative should be the same. So let's try that. Okay, so I've got it right here, and I called it Q. Call it P of X. I don't care what you want to call it. Here is the formula. I'm going to rewrite it because it's right here. But my polynomial, Q of X or P of X, is going to look like some constant plus a constant times x minus a. That just depends on where we're going to do our polynomial. Like if I want to go back here for a second, I could approximate this polynomial centering it here. Anywhere I want to center it. I've centered it at 0. As long as I'm pretty close to 0, it's a good approximation. But the minute I get over here, I'm way off. So if I wanted to get the cosine of something far away from the origin, I'm going to have to center it away from the origin. Remember when we talked a little bit about that with the ratio tests and things like that? Well, that's the linear approximation. We recognize that. And then let's see if we can model it with a quadratic. And what do you think if I wanted to do a cubic? Because you're going to be doing a cubic. You're going to have plus C3 x minus a to the third. You just follow the directions, it's not too bad. Well, what is f of 0? F of x is equal to the cosine of x. Right? So, f of 0 equals q of 0. So q of 0, what is q of 0? Now, by the way, let me fix this first. We're not going to center it at a. Where are we going to center this? At the origin, right? So this is going to look like C0 plus C1 times x. A is 0, right? Plus C2, and that's x squared. Is that okay? You got to stop me if something's not right. And so now I want you to figure out what q of 0 is, because I know what f of 0 is. F of 0 has to equal q of 0. I'm using condition 1. And by using these conditions, if I add more and more terms, I can figure out what C0 is, C1 and C2. It's not related to the geometric one. I wish it were, because then I could just do something simple, but unfortunately not. And we said f of 0 is 1, right? So f of 0 equals 1, because that's the cosine of 0. And that's equal to q of 0. And what's q of 0? It's equal to C0 plus C1 times, what is x? So it's 0. Plus C2 times 0 squared. Okay, read my writing. So what's C0? What's got to be true about these guys? It's got to be 1. I just did that. That was the linear approximation, right? Okay. So we got one of those. So what have I got? C0 is equal to 1. And by the way, I took this really out of the textbook, so then the author changes notation. He now changes it to something other than C0, but that's okay. Yes? because f of 0 is equal to the cosine of 0. Okay? Now, I know f prime of 0 equals q prime of 0. So f prime of x is equal to negative sine of x. So f prime of x is equal to negative sine of 0, which we said was, whoopsie, I meant 0 here, was 0. Okay, what is q prime of x then? Here's the whole heart of it. What is the derivative of this polynomial? We're going to use this form right now, because eventually you're going to make it n terms. C0 is what? What's the derivative of that constant? 0. So it's plus, or it's going to be C1 plus, what's next? 2C2 of x. What is q prime of 0? Substitute in 0. It's C1 plus 2C2 times what? 0. So what's C1 equal to? Q prime of 0, which has to equal f prime of 0, which is 0. Which we already kind of, well, no, we didn't know that necessarily. Okay, so now we have C1 is equal to 0. I got this one, this one. Is there a squared term? Probably. So let's look at that. So what do we have to do to get the squared term? We're going to look at the second derivative. What's f double prime of x? What's the derivative of this guy? It's what? Negative cosine of x. And what's f double prime of 0? Okay, that's negative 1. That has to be my q double prime of 0. Okay, so where's q prime? It's not that hard. Q double prime of x. Okay, I'm going to take the derivative of this one now. What's the derivative of C1? That's 0, right? Equals 2C2, right? And this has to equal this. Everybody agree with me on that? Yeah. Negative 1 equals 2C2. What's C2 equal to? Negative 1/2. Now I have the quadratic approximation. Just substitute it into this little formula right up here. I want to put it right up here. So Q of x is equal to C0, which was 1. C1 is 0. But why don't I go ahead and write it? 0 times x. C2 is negative 1/2 of x squared. So this looks like negative 1/2, whoops, 1 minus 1/2 x squared. And we're going to use our graphing calculator. So those of you who have an Inspire, you're at an advantage. I will be getting, supposedly today, I'm supposed to be getting Inspire calculators, and then anybody can borrow them if they would like. Who's got my iPad? Oh, okay. Anybody can borrow them if they'd like. What's nice about it is you can put your whole report on the Inspire, but use the, I would just get the free copy of the program for your computer because it's much easier to type. Because they have a notes page, which is like word processing, and you can type up everything you want. They've got math type. You don't have to type it, but if you wanted it all in one document, you don't go to Scratchpad, you go to the actual documents, and you start a new document. It'll be page after page after page, and you can give it to me electronically if you'd like, either via email or via link. It doesn't matter, but it's just kind of nice. But for the moment, I'm going to use my regular graphing calculator, and we're going to graph the cosine of x. Oh, I hate that. You just go to the TI website, and it's a free download. Yeah, and you can, but I'll loan you handhelds, because I have handhelds anyway. And we can look at it. It's really nice. And then I'll show you how to get the Taylor polynomials on the Inspire. The software's for free only for a month. Long enough for us. Okay. So, oh, do we have cosine? Now, what mode should we be in? Radian. I believe I'm in radian mode, but I'm going to swear to it. And I always zoom at trig. Now, part of what you have to do is this. So if you get one of the Inspires, it's really easy to print off the pictures. Or you can come and use my Smart View. But if you have the computer software, it's really easy to print off the pictures. Let's do the first approximation. That was 1, right? I have my little circle trace. It's not particularly interesting. It only works when you're really close to 0, doesn't it? I wouldn't even call it an approximation. I mean, it's a linear one, that's all. The circle thing makes it slower. And then we're going to graph 1 minus a half of x squared. Now, I really should be on the Inspire because it's in color. Also regular, because most of you have this. X squared. Okay, and I'm going to change this to a thicker line. You guys know how to do that, right? I should have these today. Yeah.
Why did you use the quadratic better for approximating zero?
Well, let's look at it. Look at it. Here comes the quadratic one. Is it a better approximation?
Yeah, but I was just close to zero.
We want to be anywhere close to 0. You're using this polynomial. The question is, are we just doing it at 0? Well, they're both true at 0. They have to be true at 0. But you're using this. You're trying to generate a power series to represent the cosine function. That's what you're trying to do. And these are called Taylor polynomials, in particular, because Taylor is the one who came up with the fact that the derivatives have to be equal, the second derivatives have to be equal at that point. And if I continue, which you have to do on this project, you know, try to do a cubic, do a quartic, and stuff like that, and you'll see what happens. You'll have to see what happens. It's part of the problems. So then what's it say? I don't have a handout for some reason. Okay, then it says, we're already done through 2. Determine the values of x for which the quadratic approximation is accurate to within 0.1. And remember when we did that a long time ago? Yeah, it's the same type of thing. So graph those things, and you'll be fine. Do you want to see what this looks like on the Inspire? Yeah, and then, see if there's anything. They want you to find, in terms of derivatives on this one, this is just number 4. This is not the cosine curve, it's any function. So you're going to have f of x in there. That's okay. It'll be okay. Then I'll give you time to work on it. So I'm going to give you time right now to work on it, but wouldn't you like to see this on the Inspire? So if you need to borrow a calculator, I do have some. I mean, I have Inspires that I don't want to color, but I'm getting the new ones. What?
What? Uh-oh. Oh.
They did something to my computer. Well, it took forever to boot it up. I ordered them. They were supposed to be in December, and they didn't come. No, I'm getting them for borrowing them. Okay, maybe. Okay. Well, I can't do it today. Now, if you give me a second, I could maybe run down and see if they've arrived. They're supposed to arrive today.